we'll only be having a short meeting today. Okay, since your topic or our very last topic is only short and quick. Okay, actually, you guys already know this one, but you know, just in case some of you do not still know what is an LV or how does it work, so we will discuss this one for today. And yeah, so this will be our very last topic, and the meeting next meeting or your our very last meeting next meeting will be your free time to finish all of the activities that I gave. Okay, so the remaining time for today, let's say we still have an hour, so we will be using that one later on to those some of you who might have a question. So this is now your chance to ask a question so we can have an hour of Zoom meeting for us to talk about your problems or concerns. Okay. All right. So uh, before that, so we will finish this one first. Okay. So without a further delay, let's start. So your chapter 7 is about light emitting diode or LED. Okay. So I hope all of you already knows what is an LED look like. So this is an LED. Okay. So we have a blue, a green, a red, or even a yellow one. Okay. So those are our LEDs. So first, you have to know what is the main definition of a light emitting diode. Okay, so this is an specialized type of diode as they have very similar electrical characteristics to a PN junction diode. So actually this is like working as a PN junction which creates light if it's in forward bias and then which completely blocks the current if it's reverse bias. Okay, so yeah, a normal PN junction diode, which only works during the positive or during the forward bias. Okay, so it will pass current in its forward direction but block the flow of current in reverse direction. So this is a typical diode. Okay, so when operated in a forward bias direction, light emitting diodes are semiconductor devices that convert electrical energy into light energy. Okay, so let me just give you a short scenario. So once the hole and then the electrons meets, so it has a capability to create photons. Okay, and then those photons are now the light energy, which emits light. So modern light emitting diodes have their cathode, which of course the negative terminal, and identified by either a notch or flat spot on the body or by the cathode lead being shorter than the other, as the anode, which is the positive lead, is longer than the cathode. Okay, so if you're going to take a look on this one, we have here the parts of the light emitting diode. So first one is the cathode and then the anode. So mostly the cathode is shorter and then the anode is longer. Okay, and then you will be able to see here the flat spot or the notch if ever there is. But mostly, okay, we don't have that flat spot or notch in here. But sometimes we do have that one. But our main way for us to verify or check whether this is the correct polarity or no is the terminals. So the shorter one is the cathode, which is the negative, and then the longer one is the anode, which is the positive. Okay, and then going further inside of the LED, so we have here the LED chip and then the reflective cavity. So those two are the main parts wherein light is coming from or light is being created. Okay, so as you can see right here, we have the anode and then the cathode. So those two wires, once there's an electricity passing those two wires, so that is from the start where the electrons and then the holes converts or creates a photons. Okay, which of course creates. And then, as you may all know, okay, it is being covered by an epoxy lens. Okay, so this one is a double purpose. So this one protects the LED chip and then the reflective cavity from, from being shaken, from vibration, and then of course to protect the LED chip and then the reflective cavity itself. Okay. So yeah, and then the other purpose of this epoxy lens is, to enhance the light. Okay, as we all know, this one is already creating the light, but the epoxy lens will enhance the light a little bit more. Okay, so yeah, that's the purpose of the epoxy lens. Okay, so light emitting diode colors. Okay, so we have here the RGB LED, wherein it can emit a combination of colors. So it could be green, could be blue, it could be red, or any other combination of colors. So light emitting diodes are made from exotic semiconductor compounds such as gallium arsenide, okay, or gallium phosphide, or gallium arsenide phosphide, or silicon carbide, or gallium indium nitride. So if you're going to mix all of them together, so you will be able to create different ratios, and you'll be able to produce a distinct wavelength of color. Okay, so it's like uh, putting different ratios to create different colors. Simple as that. So imagine that blue one is like 50%, and then green one, and then the red one is 25 and then 25%. So in that case, you'll be able to uh, create a new color. So out of red and green and blue, right? So that is an example. I don't know what is the outcome of 50% blue, 25% green, and then 25% red. So I'm not that good when it comes to combinations of colors. I only know the primary and then their basic combinations. But when it comes to three colors, which is being combined together, so I'm not sure anymore. Anyway, so for you to be able to understand this one further, so we have these their respective colors. So for the gas, which is the gallium arsenide, okay, so it has a wavelength of 850 to 940 nanometer. Okay, so basically, if it's just alone, okay, this one is the infrared. So as you can see, it's like pink. It seems pink to me. So I don't know to you guys, but this one is pink, which requires a forward voltage of 1.2 volts for you to be able to activate this kind of color. And then the second one is the gas P, which is a gallium phosphide. I think no. It's gallium arsenide. Gallium arsenide phosphide, which is ranging from 630 to 660 nanometer. So this one by default is a red one, and then it requires 1.8 volts for you to activate a red color, and so on and so forth. So as you can see, they have their own respective wavelength, and of course their colors, and then their required forward voltage. Okay, so as you mix those colors, of course, you'll be able to create uh for this one, you'll be able to create other colors, okay, aside from it. So those are just some basic colors, or yeah, that you'll be able to think of when it comes to using this RGB LED. Okay. Right, so moving on. So the actual color of a light emitting diode is determined by the wavelength of the light emitted, okay? Which in turn is determined by the actual semiconductor compound used in forming the PEN junction during manufacture. So if you want to create a certain wavelength, so you must know what is the wavelength of this specific color. Okay, so in that case, you'll be able to, let's say, you're looking for the color of green. So your wavelength, okay, must be within this one, 550 to 570 nanometers. And then you must have enough forward voltage, of course, which is 3 point, or at least 3.5 volts, right? And then therefore, the LED of the light emitted by an LED is not determined by the coloring of the LED's plastic body, okay? So maybe some of you are thinking that the epoxy lens is the one that is creating the light. Okay, I mean, yeah, or creating the color, okay, or making the color red, or making the color green or yellow. It's actually no. The LED chip and then the reflective cavity is already the one creating its color. Okay, and then the epoxy lens is just enhancing the color. Okay, so if we have a green here, so we should have a green epoxy lens. If we have a white color here, so we should have a white color for us to, you know, see a white color, because if the epoxy lens is yellow, then we will see a white yellowish color. So whatever is the color that is being created, so same is with the color of the epoxy lens. So for us to not have two colors in combination. Okay, so take note this one. The color of the light emitted by an LED is not determined by the coloring of the LED's plastic body. So although these are slightly colored to both enhance, as I said a while ago, it's just to enhance the light output and to indicate its color when it's not being illuminated by an electrical supply. Right? So at this point, did you guys get it so far? Or how does an LED work? All right. So yes, sir, coming from Mr. Brasi. How about the others? Yeah, like I already know that you guys already have an idea what is an LED like. You know the cathode and then the anode. But considering the other parts, so maybe guys still don't know those. So it is a good thing to discuss how does an LED work. All right. So it seems that most of you have answered yes. Actually, three of you. So Mr. Charles and then Mr. Reister said yes also. So I hope the others who didn't answer also understand this one. Okay. Right. So moving on. So by mixing together a variety of semiconductor, it could be metal and gas compounds. So the following list of LEDs can be produced. So we have here types of light emitting diodes. So we have the gallium arsenide, which is by default an infrared. So again, the color of infrared is not red, okay, but it's actually like pink. Okay, and then gallium arsenide phosphide is red to infrared, or sometimes orange. So depending on your wavelengths. And then aluminum gallium arsenide phosphide is high brightness red, or sometimes orange red, orange, and yellow, and so on and so forth. Okay, so yeah, mostly we have gallium and then an additional of other semiconductor, or we have aluminum and then another combination of other semiconductor. We even have zinc here, zinc selenide, which create blue. Yeah, so there's a lot of combinations here. So if you want to create an LED, okay, parts by parts, so you may want to study those semiconductor first for you to be able to create a certain color if you're trying to create one, just in case. All right, so we have here the current voltage characteristics of the light emitting diode. So again, you already know this one. So yeah, the parts, which is notch, the short lead, the longer lead, the anode, the cathode, blah blah blah. And then if you're going to take a look on this one, so we have here the graph of the current and then the forward voltage. So as you can see right here, the white one requires more forward voltage than the rest. Okay, so the first light that you'll be able to create, which is ranging from say, I think less than one. I don't know. It's 1.2 actually. So 1.2 volts, yeah. So the minimum is 1.2 volts, wherein you'll be able to create the very first color, which is the infrared. The next one is the red one, the amber, the yellow, green, blue, and then white. So the hardest uh, color to attain is the white one. Okay. So we this one, yes, Miss Kagadas, you're raising your hand.
Sorry, sir, napindot.
All right. Okay. So as you can see right here, again, the white one required more forward voltage than the rest. Okay. So anyway, this is just for you to show that the white one is the uh, hardest to attain when it comes to creating a color. So not actually the hardest, but uh, the color or an LED color that requires more voltage than the others. Okay, so usually, okay, this is very important. So not only having an exact forward voltage, but of course you must also have the correct current. Okay, so it should be only ranging from 10 to 30 milliamps. Okay, so actually having 15 milliamps, okay, or 10 is already enough on any of those colors. It's just that you must have the sufficient forward voltage for you to, power up that LED. So the voltage is the one that is powering up the LED to make it work. And then the current is the brightness, okay, of our LED. So if you have a lower current, okay, of course, the dimmer it is. But if we have the exact or the they call this one the minimum standard of current for that uh, LED, so you'll be able to get the uh, highest brightness. Okay, so depending on your current. Okay, so we have here the LED series resistor circuit. So which is actually kind of the same with our uh, normal diode. So we have here the voltage source, the series resistance. So initially it already has a resistance, but it's only minimum, okay, like very minimal, okay, which still requires what's one an external resistors. That is why when it comes to LEDs, we still need to put an external resistor. Okay, so we have here the LED itself. Okay, which is the polarity is the anode first before the cathode. Okay, and then before this LED, we have here the series resistance wherein I think very minimal, like 0.00. Okay, by default, okay, it already has a minimum resistance, but 0.00 something. So it's like not having a resistance at all. But it has a resistance, but just a very small. So that is why we still need to put an external resistance for you to be able to, control the current that is going to pass through this LED. And then we have here the forward voltage across this LED, right? And then we have here the formula for has to be able to know what is the required resistance of this certain LED. So again, we already have the reference wherein for the current, it should only be ranging from 10 to 30 milliamps. Or mostly, okay, it should be 12 to 20 milliamps. Okay, and then for the series resistance, so that depends. So sometimes it's 100, it's 300, and so on and so forth. And then we have here the current of the resistance, and then the current of the LED or the forward bias. So as you can see, whatever is the current that is passing here, which will also pass here, it's or they are actually the same since they are in series connection. Okay. Right, so moving on. So we have here an example. So light emitting diode sample problems. So when it comes to problems of LED, we only solve for the RS, VS, or VF, or IF. So as long as you have the other variables, so you can solve either of those missing variables. All right, so let's start. So an amber colored LED with a forward voltage drop of 2 volts is to be connected to a 5 volts stabilized DC power supply. So using the circuit above, this one, the default circuit of the LED, so calculate the value of the series resistor required to limit the forward current to less than 10 milliamps. So it is now requiring us to have 10 milliamps or less than 10 milliamps. So we should get a correct resistance wherein the current is 10 or less than 10 milliamps. And then another one is calculate the current flowing through the diode if we have a 100 ohms series resistor that is being used instead of the calculated resistor. So the first one is this one. So we can already use this formula. So Vs is 5 volts minus the voltage drop, which is 2 volts. So that is the required or the forward voltage that is being required by this LED, which is the amber colored LED. Okay. So divided by 10 milliamps. So whatever is the computation there, that is the resistance that you'll be needing for us to have a 10 milliamps of current. Okay. So here's the solution for number one. So 5 volts minus 2 volts divided by 10 milliamps is equal to this one. So as you can see, we have 300 ohms. So number two, it is now asking us the current flowing through the diode if we have a 100 ohms series resistor. So just recall this one, just use this formula and then, just put this one here and then the RS here. So it's like interchanging for us to be able to get the formula of the current. So say Vs minus Vf is 5 minus 2 divided by 100, which is the series resistance. So as you can see, is now, or we now have a 30 milliamps. So the safe resistor that you can include here is ranging from 100 to 300 ohms. So less than that or more than that is not within the range of the LED anymore. So take note, this is the safe point, okay, wherein for us to be able to say that your your LED, okay, will uh, uh, work longer, or its lifespan will be longer if you have this range of resistors or resistance. Because if you have lesser, there's a higher chance that your LED will uh, will not work. Okay, and if your resistor is higher than 300 ohms, okay, so there's a chance that your LED uh, will pop out. Okay, will get burned. Okay, because ah did I no, it's the opposite. Okay, if you have a less resistance, there's a chance that it will pop out because it is receiving more current than the normal range. And then if you have a higher uh, resistance than 300, then your LED might not get power up. So it might not be able to create light, right? So connecting LEDs together in series. So as you can see, before we only have one, but now we have two LEDs. So we can connect LEDs together in series to increase the number required or to increase the light level when used in displays. So as with series resistors, LEDs connected in series all have the same forward current flowing through them as just one. So as all the LEDs connected in series pass the same current, it is generally best if they are all of the same color or type. Okay. So actually we have the same formula. It's just that instead of having one voltage drop, so you just have to multiply it by, let's say if it's 2 LED, then multiply it by 2. If it's 3 LED, then multiply it by 3. Okay, so the same. Let's say, assuming that we have a voltage source of 5 volts. Okay, and then we have 3 LEDs. So just multiply it by 3. So let's say the voltage drop is 1.2 volts. So just multiply it by 3. So 3 times 1.2 is equal to 3.6 volts. So that is now the forward voltage that you need at least for you to be able to power up those LEDs. So let's say we are trying to solve for the series resistance, okay? And of course, we will put here by default the 10 milliamp because that's the minimum range for our current. So you can actually put here 15 milliamps, 20 milliamps, or up to 30 milliamps, okay? So Vs minus Vlad is equal to 1.4 volts. So 5 minus 3.6 is 1.4 volts. So 1.4 divided by 10 milliamps is 140 ohms. So if you want to have a current of 10 milliamps, so you must have 140 ohms of series resistance. Okay. And vice versa. Let's say you want to have 20 milliamps, then just change this one, and then you'll be able to solve the series resistance that you want to have. All right, so that's actually it already. So I will not be giving an activity for this one anymore since this one is super easy. Okay, all you need to solve are the RS, the VS, VF, and then the IF. So as you can see, we only have one formula. So just by manipulating this formula, you will be able to get the other uh, this one variables. Okay, as long as you have the other variables. Okay, as long as one missing only, and then the others are not missing. All right, so here are my references where my lectures came from. And then here are some helpful videos in understanding how an LEDs work. So as you can see right here, we have a Hindi version. So I've included this one because he's the only one that explains how does an LED work step by step. Okay, like in full explanation. But if you want to have an English version, so you can watch this one instead. But uh, actually, you can already understand what he is trying to say because it's already written in his notes. It's just that he is explaining it in Hindi language. But the notes that he is trying to show is an English one. So you'll be able to understand this one without hearing what he is trying to say. But just in case you don't understand what he's trying to explain, so you can watch this English version instead. And then how this is a video on how does an LED works. Okay, so that is it for this chapter. So yeah, so we still have part 2 and part 3. Okay, so I will be opening that one to those who has a question or clarification. But if you don't have a question or clarification, so you may not join our part 2 or part 3 anymore. Okay. So yeah, that's it for this module 7. So any questions so far? We still have 30 seconds, I guess. All right. So no one's talking. I don't know if you guys have understood. Anyway, I will be opening the part 2 later on. So to those who has a question, so feel free to join the part 2. Okay. So none coming from Mr. Barasi.